the week after, we're gonna do the last week of classes, we'll do a mock exam. We'll go through these. We're gonna get you guys prepared. I know I'm like releasing stress, but we're gonna get you guys up to date, don't worry.
We want you to be stressed now and not right before the final, so we'll get you not stressed before the final.
So the reason we're saying it is just, I don't want you guys to write the final and then sit and be like, what was that kind of thing, and
Yeah.
whatever. But, so, we're just gonna get you guys as prepared as possible. But those are the 5
Oh, there's the question.
things. What is that?
Oh, it's like if you guys ask us questions.
Oh, yeah. Also, because we're also making these slides from our own thoughts, some of the questions you guys might ask, it might have run across my mind. So please do not be discouraged to ask them. Like, ask them. I'm gonna be honest with you, tell them I don't know what the answer is, but I will give you the answer. So I'm not gonna leave you to it. So I just want you to not be discouraged if we don't have an answer to the spot. Sometimes it doesn't even cross my mind, the
Yeah.
concept that you're bringing up.
But we will get back to you on those questions, for sure.
Okay, did I cause more stress? Yes? Anyways, okay, we're gonna get into renal today. Did everyone like the fetal review? Yes? Okay. We did go a little bit in detail, but I think it was for the better, but, this one is gonna be hefty. Gonna be a lot of stuff to cover. There's probably 3 lectures that he thought that we're gonna cover today. So just bear with me. I'm gonna go as slow as possible and try to get you guys up to date. We did receive some emails prior, and
So hopefully we'll answer them in the lecture. If we don't, definitely come to us at the end and let us know, and we'll try to explain it better to you in person, or we'll send you an email with a better explanation.
yeah, I think we got a question about the positive loop and counter current.
Current exchanges.
So we'll talk about those, but if it still doesn't clear up any confusions, please come talk to us after, okay? Alright, I don't think there's anything else. Okay, we're gonna talk about 3 guidelines today. I'll do anatomy and functions, and then we'll talk about filtration, and then its clearance, and then we'll move on to do how to measure it. Okay, so, anatomy. Before we get 3 functions, pretty straightforward. Kidney filters, regulates, and produces. That's the easiest way to remember it. Filtration, regulation, and production. Fill in the blanks afterwards, okay? So what could it filter? Probably waste. Then it regulates electrolytes, and then produces hormones that, at the end, regulate blood pressure and blood flow, okay? Pretty straightforward, nothing too intense. The anatomy of the kidney might be complex when you look at it, but I'm gonna go from the outer to inner, so I'll talk within, okay? So, starting from the outer point, we have the capsule, which is right at the edge. These kidneys are shaped as a bean, as you can tell, and they are non-distensible. That means it's rigid, it can't expand, it doesn't change its shape at all. Unlike the lung, you have that tissue that it allows it to do that, this one doesn't, okay? The same shape, otherwise, if it was distensible, because of the huge blood flow within it, it would explode, okay? Because there's just so much happening. So, you have this capsule, and then you have 2 layers afterwards. The first one, you have the cortex, which is this grainy part, and then you have the medulla, which is the non-grainy. Does anyone know why the cortex is grainy? Yes. Lovely. That's such a good feeling. Nice. Okay, so because of the tubules and the glomerulus in the cortex, which we'll get into later, due to that, there's these complicated and different shaped of these tubules that cause this grainy looking aspect, whereas the medulla doesn't have the glomerulus within, so it's very, should just look.
Should have left it.
It doesn't have that glomerulus, so it's smooth, it doesn't have those grainy aspects, okay? That is it. That's essentially all the cortex. This medulla, what's important about it is that you have 8 to 18 of these in each kidney. They vary, but you have these pyramids, these renal pyramids, like it's called. And the base, it's on the cortex side. It's not at the tip, it's the inner, the base is at the cortex. Okay, so on your exam, or whatever it is when you're referring to it, make sure to use the right terminology. Because if you say the base and you're talking about the tip, like, you can just be comfortable with that, okay? So at the base is at the top, and then you have the tip, which there's a duct within the medulla with each pyramid. And this duct is actually not really visible to the naked eye. And that's where your urine actually flows into, okay? After that, that flows into your minor calyces, which in this image, this yellow is where the urine is filled in. You have the minor calyces, which is just the subdivisions of the major calyx, okay? And then from the major, you have the pelvis, and then which goes into your urethra, okay? What the pelvis, renal artery, and the vein fall within is this renal sinus, which is just this shallow hole that these tubules can flow into, okay? If you're referring to the hilum, you're referring to 3 things: the pelvis, artery, and vein, okay? So, talking about it as a review, you have the capsule, going to the cortex, going to the medulla, minor, major, renal, hilum, urethra, okay? That was the simplest way I could, you can refer to the anatomy of the kidney. Anyone have any questions? We're good. Sweet. Now we're going to talk about the vasculature. So I'll talk about the renal circulation, okay? So the cortex is the pink area, medulla is the white. So those tubules I talked about that makes it grainy is due to these, and so how complicated they look. Now the medulla, I forgot to mention the medulla, why it's not grainy is also because it's not because they don't have these tubules, just because they're aligned as parallel arrangements, okay? That's what makes it non-grainy as well. So the flow, we have about 20% of the cardiac output going to the kidney. Now, the important part of the whole thing is that you need this high blood flow in order for ultrafiltration to happen. That's what you need. That's what's necessary. Now, how does the blood get in there? So, you have the renal artery, gives rise, to these arcuate arteries, and then those arcuate arteries go up, give rise to these interlobular arteries, which isn't, like, you don't need to know that, but just know that that's the stem, essentially. So you have the renal artery goes to arcuate, then goes and gives rise to these afferent arterioles, okay? Afferent arteriole gives blood to the glomerulus. That's the first capillary bed. The glomerulus, blood exits through efferent arteriole, and then that goes to the second capillary bed, which is your peritubular, which is mentioned here, but it's basically these kind of intertwining on the sides. And then that's it, through those capillaries, that's where the blood is drained into the renal vein, and then ultimately exits. So it's a portal system within this very small space. So as you can tell, another reason why I said it could explode is because if you don't have this rigid capsule, this high blood flow that's going into the cortex will expand, and then ultimately it's going to cause some sort of rupture. So that's why you need that capsule to have those within that layer. Now I have some stuff on here about resistance and pressure. We're going to keep talking about it so much today. I hope it sticks in your mind. But just starting from now, just know that arterioles, both of them, have the highest resistance, okay? And then the capillary beds control pressure. So arterioles control resistance, capillary beds control pressure. Where your glomerulus capillary bed has the highest pressure, but the peritubular has the lowest. Now, why glomerulus has high, we'll get into details, but the reason for that is because you have two arterioles. So usually in a capillary, you have one arteriole going in, and like that's it, that's the capillary. There's nothing else, and it's just drained through the vein. Whereas here, you have one arteriole going in and one arteriole going out, so you have the highest pressure in the capillary. So that's the reason for that. And then the peritubular, since they get drained by the vein, they don't have that second arteriole, so they don't have that high of a pressure as the glomerulus capillary bed has, okay? Now, hinting at the Starling equation, the Starling equation is probably one of the important concepts to learn. Now, teaching, the way textbook does and we do is, we teach it through the anatomy of it. Because if I were to teach you that Starling equation, it's all physics, and for my mental health and yours, I think that's better not get into, okay? So I'm gonna explain it through the anatomy and the functioning and what controls what. So, the arterioles control the hydrostatic pressure, okay? That's what they control. So in the Starling equation, what affects the hydrostatic, which is the first difference, right here? That first difference is controlled through the arterioles, through this vasodilation and constriction, which we'll get into.
So, based on what Amarala just said, I have some questions for you guys. So it's kind of out there, I mean, if you don't know it, it's okay. But what do you think the relative resistance is like in the kidney based on other vascular beds in the body? So other vascular beds, meaning capillary beds in the cardiac system, for example. How do you think the kidney is relative to that? I mean, you can just literally throw out any answer, even if it's wrong, it's totally fine. I just want you guys to like think about it. Yeah?
So it's very high because it receives 20% of the current output and it has to protect the capillaries from exploding from the huge volume.
So it's right as well. Any other thoughts on this? Okay. So I want you guys to think of the renal system as a circuit. Now, I know physics is ugly and disgusting, but resistance in the nephrons are higher. Now this is because the capillary beds, or the efferent and the afferent arterioles in this system are in series. So if you have resistors in series, you have a higher resistance. Now, what do you think the pressure is like in the glomerulus, the glomerular pressure, based on this understanding? Sorry?
Yes.
Yes. Why do you think, why is it high? Listen, I don't know who says high, so I don't know where it's
Yeah?
So we have more, or because the resistance is high, so it's in there longer and it's harder to get through those and there's no pressures on the wall.
Yeah. I like your thinking.
So-
Not quite, but you're there.
It's almost there, but. Alright, so you have higher pressure because you have two resistors in series. So you have the efferent and the afferent arterioles, and two resistors in series would increase the pressure in that circuit.
So, so those two questions are just out of the blue, but just notice how those two questions kind of don't have anything to do with what you've kind of maybe learned, but it's more about using what we've taught you guys, or at least said out loud, using that to answer these kind of questions. So if you're wondering what type of questions will be on the exam, it's just conceptual kind of questions, where you'll have to use the knowledge that you have on the renal, vasculature, and circulation, and then apply it to if this happened, what would happen. So you have to integrate these thoughts, okay? So that's just a little hint of how you have to use the information to get to the answer. Okay, so, going a little bit deeper, we have the nephron. So now we have the lighter colors, the cortex, and the darker it gets, we're in the medulla. So as you guys may know, this is the basic and functional units of the kidney, because this is where everything happens, all the filtration, how the blood is filtered, how your urine is created, it's all through the nephron. So, what is a nephron? Nephron consists of a glomerulus, which means just a cluster or capillary of blood cells, or blood vessels, I should say. And then you have tubules that are attached to it, okay? So exactly what we see here. So you have this red thing is your glomerulus within your Bowman's capsule. And then you have the tubules that are attached to it, that go around. You have two different nephrons. You have the superficial, by the name, it's more towards the top, it's more superficial. And then you have the juxtamedullary, which goes a little bit deeper into the medulla. And just like how I said on Thursday, the names are honestly just like, if you know the anatomy, names are a little bit easier to understand. So juxtamedulla, juxta is just because the nephron is sitting on top, the juxta apparatus. And then you have the medullary, which just because it goes deeper into the medulla, okay? Now, urine is formed by ultrafiltration, which means filtering solutes out of blood, essentially. So the sugar, or the endogenous or exogenous solutes that we don't need are filtered out. And the process is, so you have the you have the afferent arteriole, goes into the glomerulus. That's where the filtration happens. So, through this glomerulus, you have filtration coming out into the PCT, which is your proximal tubule. It's divided into two segments. You have the straight segment and the convoluted. Convoluted is the first one, the purple, and then you have the blue, which is the straight. So you have the proximal tubule, then it goes down the thin, descending loop of Henle, thin ascending loop of Henle, and then thick ascending. So this is your loop of Henle. So it goes down, and then it goes up through it ends at the thick ascending loop of Henle, enters your distal, enters your connecting, and then your collecting. Okay? So these are abbreviations. So PCT, proximal, convoluted, proximal straight, thin, descending, ascending, thin, ascending, and then you have thick, distal, connecting, collecting. Is everyone good?
Alright, so based on what you know about the nephron now, why do you think that we've evolved to have tight junctions in the nephron?
So think about what's the function of a tight junction. When you think about Bio 120, you have three types of junctions. What's the function of the tights?
Someone just shout it out if they know.
Think about it. They're tight. So they're connecting. There's a little space between.
Nothing gets back in.
Or more like nothing gets through.
Back in.
Through. Okay, you got it. Go on.
Alright, so then if we have these tight junctions in the nephron, what do you think it's doing if nothing can get through? So having all these tight junctions prevents the leaks and forces all the contents to move through the cell. And if we were to have free flow where there were no tight junctions, this process that the renal system has, it wouldn't be regulated, essentially.
Okay. So, a little bit more, even in depth. Renal corpuscle. This is that glomerulus we talked about earlier. You have the Bowman's capsule surrounding it, Bowman's space, and then you have the capillary, or glomerulus. So that whole thing is called renal corpuscle. Now there's two layers. There's a parietal layer, which is around the capsule. You can see here. And then you have space, and then you have the capillaries. The second layer is actually not right after parietal, it's on top of the actual glomerulus. It's the visceral layer, which is created through, anybody know? How's the visceral layer created? Yes, lovely. So the podocytes, I'm not gonna go into detail, but through their foot processes, they kind of wrap themselves around these blood vessels, and they create that second layer as a protection, okay? Now, within this layer, you have 4 different filtration barriers happening, okay? The first is the negatively charged glycoproteins, okay? So glycocalyx, that's your first barrier. Second one is your endothelial cells, and then you have your basement membrane, and then you have the actual podocytes. So you have 4 different barriers that take the solutes out of the blood into the tubules, okay? We'll get into the more function of these a little bit later on, but that's basically the basis of the renal portion. Now, everything's exited, filtered out, they enter the tubules. So, like Abby said, this diagram, by the way, I think it's the most simplistic diagram in terms of, like, if you want to just review and study, this is the best one. Where on the left side you have your vascular elements, and then on the top you have your actual tubules. So you have the bulbous capsule, and then you have filtration happening. And just keep in mind, note that the vasculature is going along with the tubule. Now we'll get into detail why that's important, but that is crucial. The anatomy of the renal system, it's the reason why it functions. So in other words, if these tubules, if this loop of Henle was a little bit wider and it wasn't so tight together, it would not be able to function. So this is probably one of the organs that the anatomy actually is directly related to the function of the actual organ. So, proximal tubule, as you can imagine, it receives the largest portion of the filter and has the leakiest epithelial junctions. So that means that it doesn't have tight junctions, right? The tight junctions would make it less leaky. So this one has the left, not that doesn't has less. So, like I said, you have endogenous and exogenous solutes that leave the capillary, that enter the tubule. Everything else still is in the blood. Sodium, bicarbonate, nutrients, ions, everything's still in the blood. Now we enter the loop of Henle. So the loop of Henle's function alongside the counter current multiplier exchange, alongside that, it actually creates your concentrated urine. That's its function, okay? That's where your urine is that's where urine is essentially created. That's where it's concentrated, okay? And that's all you need to know. Forget about the sodium, we'll talk about it later. But that's where the urine is concentrated. And then you have the collecting and the distal and then collecting. And the connecting is actually, should be between that, but that's, again, just by the name, it's connecting. It doesn't really have any function. It's just a loop that connects the two together. But in terms of functioning, the collecting duct and the distal, they do the fine controls at the end through water excretion and electrolytes, and then finally the collecting duct actually can exploit the hypertonicity of it too as well. So if you, for example, if you have too much water, it will come into effect and remove. If you have less water, come into effect, fix them. Yes?
I found in the textbook that there was like lots of specifics about like which part like deals with sodium and which part like reabsorbs water. Is that super crucial to remember all of that, or is
For
it
your
more just
understanding?
generalized understanding?
This is the most, like, this is the simplistic way of just explaining it.
Okay.
But you're right, those segments, like, for example, in the textbook, in the proximal, if you read, it goes through like S1, S2, and S3, and then the S3 is actually the straight. It talks about what goes through where. That is, it's a textbook essentially, so it goes way into deeper than you might need to know. But if you completely want to understand how everything moves, that probably, reading that might be to your best benefit. But in terms of like me explaining it now, those are all true, but I'm just giving the most simplistic way of explanation. So that was all the tubules, okay? So we end off, and then that from the collecting goes to the duct that I said we couldn't see, and then that's where the urine exits. Going back to that renocorpsule, beneath it, or more like attached to it. So if we, sorry. So here, in the actual, I want to show you guys the actual picture here. Okay, here. So in this box, this is the thick descending going up, okay? Right here, the thick actually attaches to the corpuscle. And it does that through the juxtamedullary apparatus, okay? So it makes contact with the thick ascending, and it has two functions. It's essentially a regulator. So if you can imagine this, halfway through the, if you say racing track, halfway through it, it's a regulator in there where it senses the fluid and the sodium reaching, so it has three different types of cells. The denser cells, granular, and then the mesangial. If the sodium reaches the denser cells, it adjusts the filtrations, okay? If there's too much sodium, adjust it. If there's too less, adjust it. And then at the end, the afferent arteriole, by vasodilating, and therefore affecting the hydrostatic pressure, I'm just trying to get that into your brain. By dilating, it stretches, and that stretch stimulates, sorry, my bad. By constricting, it decreases the stretching, and that stimulates the apparatus. When the apparatus is stimulated, it releases renin, which I don't know how much you guys know about renin, but it's just the pathway that controls your blood pressure. So in other words, when it's stimulated, when the apparatus is stimulated, it helps out and regulates your blood pressure as well as a function. But the most important thing is that JGA is a regulator midway through the tubules, okay? So that's the anatomy and function of the different parts. Now, when we talk about filtration, we're gonna obviously touch base on every one of those tubules again, talk a little bit more deeper in what everything does. But that is the overall gist of the first objective. Is everyone with me?
Okay, cool. So let's go into the glomerular filtration. Oh, you can hold it. I only have 1 second. So, so having high glomerular filtration is very essential so our body can maintain this stable and optimal extracellular levels of solutes, which include toxins, and water. So compared to other organs, the kidneys receive a very large amount of blood flow. And within that blood flow, there's a very high amount of that blood flow that's being filtered. Make sense? So under normal conditions, our glomerular filtration rate of 2 kidneys is about 180 liters a day. And
Just put that into perspective for a second. How much you're filtering every day. 1 liter, looking at it, is enough to kind of, this is 1 times 180, okay?
And theoretically it's not really an exact number, but from that 180 liters a day, you're probably cleaning out like at least like a liter or half of that. Or you should be, if you drink a lot of water. So why do you think
Oh, my bad.
so why do you think there's such a large rate of filtration that's required? Anyways, the answer is there. So it's to expose the entire extracellular fluid frequently. So we want to have a very high turnover so that more of that volume of toxic material leaves the body. Now, what would happen if there was no urine? Does anyone know what would happen if we didn't have these toxic materials moving out really fast or in high volumes? Anyone?
Build up in toxins in the body.
Essentially. toxic material, and it would cause a delay in the excretion of it. So having this high blood flow and this high glomerular filtration rate allows the kidney to release, or like to eliminate all that toxic material that our body produces or has.
And then it goes back to the first point I made where you need that high blood flow. This is just covered, make it more sense, okay? So you need that blood flow so you can excrete these toxins. Okay, so those 4 barriers I talked about, except endothelial cells, the other 3 they consist of charged negative glycoproteins, okay? And this is kind of pretty simple. The 3 things that you would think would affect filterability of these solutes would obviously one would be size. So the larger and the more heavier you are, it's less filterable. The electric charge has an effect on it. So these penetrations so between here, these slits have those glycoproteins. So that you have this selection of what molecules that are negatively charged goes through. And the third thing is your size, your shape. So the more rigid and the more globe-looking molecule is, the harder it is to go. Okay, pretty simple. Now we're talking about the Starling equation. Okay, so the physics behind any fluid movement over capillary walls is the same. Starling forces contribute to everything. But in the glomerulus, it's different because the filtration rate exceeds other regions, and that's due to having stronger Starling forces. So your hydrostatic and colloid osmotic are stronger, and then the permeability is higher, which means more can go through, okay? Colloid osmotic is different than osmotic pressure, okay? So when you're referring to these, please make sure you either say the full name, because if you just talk about osmotic pressure, you're talking about a whole different thing. So you need to state colloid osmotic. Or I think on the textbook somewhere else it says oncotic as well. That's also synonym to what that says. So oncotic or colloid osmotic is the same thing. Just make sure to state the full thing, because you're talking about a specific thing here. Now, hydrostatic pressure, like I said, what are they controlled by? Come on, think about anatomy. What goes in the glomerulus? Say it. Who said it? Say it out loud. Somebody said it.
Arterioles?
Yes, thank you. So your arterioles, afferent and efferent, control your hydrostatic, okay? So they're vasoconstriction and dilation. Do you want to open the door behind you? Sorry. She was just standing there. Okay. Okay, so your hydrostatic pressure is controlled through that. However, your colloid is controlled through the production of your proteins. More protein, higher colloid pressure. Less protein, lower the pressure. So it's directly integrated to each other. That's the simplest way to describe the equation. So, what we want is ultrafiltration. We want the solutes exit, and how that occurs is through hydrostatic pressure difference, which means PC minus PFI, or PIF, needs to exceed the colloid pressure. If that is the case, you're going to have ultrafiltration. If that's not the case, you won't. Okay? So in a regular body, most of the time this is the case, where your hydrostatic pressure is exceeding your colloid. But there's the time where you might need the colloid to be higher, you might not need to filtrate as much, so then it reverses. Does that make sense? Yes? So, now, going a step further, you need correlation of these two to be correct. So, to filter things out, you need the hydrostatic and the glomerulus to filter out. Or you need the oncotic and the Bowman space to be higher. So, these greens, if you were to look at the diagram, like I said, the difference of hydrostatic needs to be higher than on colloid for it to filter out. Whereas in the Bowman space, to not have anything filtered, you need the hydrostatic to be lower than the colloid. Okay? So I have it written down here that if my words didn't make sense, if you read these, it should hopefully make sense. Okay? So essentially, what's important is that the pressures need to be acting within the right location for ultrafiltration to occur. Okay? You're with me? So please point out if it doesn't make sense. I'll repeat it. Okay.
Alright, so let's talk about renal blood flow. So having increased glomerular plasma means that there's an increase in filtration. So at low glomerular plasma flow, which is the top, you'll have the filtration equilibrium will occur halfway down the capillary. So what does that exactly mean? It means that I lost my train of thought. The equilibrium for low.
Increase plasma, increase filtration.
Okay, so you have low plasma, you decrease filtration, and having higher glomerular plasma means that there's an increase in filtration. So that's essentially what you need to understand here, that as your blood flow increases from low to normal, the site of the filtration equilibrium shifts. So kind of think of it in chemistry where if one thing increases on one side, you need it to shift to the other side. So in this case, the equilibrium will shift towards the efferent arterioles when the glomerular blood flow is increased.
So in other words, exiting everything out because there's such a high renal blood flow within the glomerulus, exiting everything out through the efferent artery.
Yeah.
The graphs we thought were easy to explain. Clearly not, because I even got confused trying to read through it. So, if you want to understand, the graphs won't be used on anything. So, but if you want to understand renal blood flow, the graphs essentially, just read that section textbook. But the important thing about it is that the more blood you have, the more filtration is going to cost. Okay, so building on that thought of the function of arterioles, they also have an effect on the flow and the filtration. So just like how we said, the greater flow, the greater the filtration, afferent and efferent arterioles have control over that, okay? So this graph, I won't point that out. Like how we said, the pressure drops through these arterioles, okay? Through the high resistance. However, glomerulus is high and constant. That pressure in between stays as it is. And that's due to the resistance that we talked about earlier. But how it should look like is how the peritubular capillary looks like. How it drops slowly, that's how a normal capillary looks like in terms of pressure-wise. But because of those two arterioles, one coming in, one going out, it stays constant and stays high. Okay? This concept here I wrote down at the bottom is probably the most confusing thing, but I'll try to explain it through a graph. If you have an increased afferent arterial resistance, this slope will become steeper, so it'll become lower. Which means your constant from there is going to move down, which means the filtration that's going to happen is going to be less. Okay, so which means you have a decrease, right? So if you increase afferent, it's going to decrease filtration. However, if you decrease efferent, if I were to increase it, it goes lower. If I were to decrease it, it goes higher, right? So you have a less of a steep, and then you have more filtration. So you have the increase in GFR. Okay? I hope that makes sense. Okay. Now, moving on to the capillaries. So that was the first capillary we talked about, glomerulus, the pressure happening in there. This is going to more be talking about the hydrostatic pressure and the colloid and what happens to them. So the capillaries, like I said, in a regular capillary bed, you don't have those two arterioles. So here, peritubular is unique because you have an efferent arteriole coming to it. And then it provides nutrients and reabsorbs fluid through the tubule, okay? So that's where the nutrient is given and reabsorption happens. Now we'll talk about that large net absorbed pressure the next slide. But what's important is that you have this glomerular filtration concentrates plasma proteins, okay? So if you have a lot of plasma proteins, which of the pressures does that increase? Hydrostatic or colloid? Thank you. So now, you have the 25 colloid going to 35. Okay, so it's increased. And then where the resistance, because we have the arteriole has the highest resistance, as we talked about earlier, the resistance causes the hydrostatic pressure to fall drastically. So it goes from 47 to 20, almost becomes more than half. And then it enters the peritubular, which will decrease it a little bit, as you can see, but it has a low pressure, so it doesn't have that much of an effect, but it moderately decreases both. Okay, so the change of pressure within the two capillaries, one is caused by colloid, one is caused by hydrostatic.
Alright, so kind of just like continuing on with what Amarala said about the peritubular capillaries. So these capillaries are subject to any alterations that happen in the arterial resistance. So let's look at this little flow chart as an example. So if you have the volume expanding, this will inhibit the renin-angiotensin system. And this would lead to a large decrease in the resistance of the efferent arterioles. And therefore, it would cause this rise in hydrostatic pressure. So the fall in the total arterial resistance causes a rise in the renal plasma flow that is larger than the increase in glomerular filtration rate. Now this means that then there is less filtration because the renal flow is a lot more than what's actually being taken out. So this causes this fall in the filtration, and more fluid will remain in the glomerular capillary. And the blood that enters the peritubular capillary has a decreased oncotic pressure than it normally would.
So this is kind of just explaining the slide that we went through. So, but this flow chart is just talking about how it's entering the capillaries, the peritubular, okay?
So when you have this like low colloid pressure and this high hydrostatic pressure, you're gonna have this decrease in interstitial fluid that's in there.
Okay, and then the last thing to talk about is how the blood flow is regulated. So, the afferent arterioles essentially the cardiac response. So what you want, how you regulate, just like we talked about in the fetal, you want to constrict the blood vessel. So here, the afferent has the ability to do that. So one response is through that, okay, through it constricting. And then you have the feedback through JGA, which again, those denser cells we talked about, if they sense an increase in filtration rate, they contract afferent. And if they also sense that ATP or adenosine is getting released over, if there's an increase of it more than the regular state, it will again cause vasoconstriction. So through two different methods, it causes vasoconstriction. That's how you regulate the blood flow. Are we good?
Okay, so now we're gonna shift gears a little bit.
Honestly, if you catch your breath, if you think you have a question, ask now, because we're gonna a little bit move into a little bit different path.
Okay.
Can you go back to that slide with the graph?
Yes.
The next one. Yeah, this one. So you explained how if there's a higher afferent arterial resistance, the slope would be steeper.
Mm-hmm.
Could you explain that bottom part where if there's a decrease in efferent arterial resistance,
Okay.
how that works?
So take that concept of what would happen to the increase in afferent. It would make it steeper. So if I were to decrease the afferent, it would make it less steep. So take that concept, put it into efferent, okay? If we were to decrease it, we'd make it less steep. Okay? Now if we make it less steep, you have more of a filtration happening. So I'm gonna bring physics into this, okay? The inner of the graph, the box in underneath the graph, is talking about the surface area, okay? The larger the box, the more filtration. The less filtration. So if we were to decrease efferent, we're raising this slope, which means we're enlarging the box, which means we're increasing filtration. Does that make sense? Are we good?
Okay, so we're gonna shift to epithelial transport. Now, Dr. Yanowski loves this stuff. I know, I feel like a lot of you guys might have been confused during the lecture. But I'll try to simplify it. Essentially, what he's trying to get across by teaching you guys epithelial transport is that the basics of how cells, how things move at the epithelial level will help you better understand how water balance and stuff works in the renal system. So the important thing to know is that the transport is governed by a law of thermodynamics. So we'll look at an example of non-coupled transport. Now this means that substance X is not directly coupled to any chemical reaction or any movement of another solute. So it just moves in by itself. So there are two driving forces in epithelial transport. The first is concentration. So if the concentration of X is higher on the outside than on the inside, we'll have this concentration gradient that will act as a driving force to move X from the outside to the inside. Good so far? Now the other thing is a voltage difference. So if there is no concentration difference between what's on the outside and the inside, but there is a voltage difference, say the voltage is higher on the inside, it'll shift towards the outside. So kind of think about it as in chemistry, when you add something to the reactants, it's going to shift to the product side and vice versa. So think of it like that. That's essentially what he's trying to get across here. That
Also here, this graph is just trying to support what Janet just said. So if you have too much going to this side, something's going to counteract it to make it less and make it cause equilibrium to happen. Okay. But the simplest way to memorize this or understand it is through the equilibrium concept. One side is larger than the other, it shifts to create equilibrium.
now, regardless of how X moves through the membrane, the direction of the overall driving force that acts on X determines the direction of the net transport. So if concentration is higher on the outside, it'll shift towards the inside, and vice versa. So some key terms, I guess. So if the X is moving across the membrane in one direction, it's unidirectional flux. Now the sum of two unidirectional fluxes is the net flux. The And the net transfer that occurs only happens when there is a difference and these two fluxes are different than each other. Are we good so far?
So here, unidirectional, just this arrow. Here, we're talking about nets, when you combine the two.
We good? Any questions about that? That's essentially like, I broke it down as much as I could, that's essentially what he wanted you to know. So now we're just gonna go into water balance. So, I'm gonna shift your attention to this little draft, please. So, yeah, sure. Okay, so at the beginning, you have this equilibrium. So it's like a steady state. Does anyone know why that might be?
It's talking about the proximal tubular, right?
Okay, so essentially, if 70% of sodium, for example, were to be in the proximal tubule, you have 70% water as well. So it's going to be equal, that's why there's an equilibrium. That's one part of this graph that's important to know. Now the next part is this area near the medullary collecting duct. Now, this is what happens. There's going to be a signal that signals for reabsorption of any leftover water. So you'll go through this whole little loop of Henle, come here, and anything that's left over will get reabsorbed, and you'll get this very highly dilute urine.
So going back to the functions I was talking about, the anatomy, I'll get to your question in a second. When we go back to that, I said the collecting duct at the end does the fine controlling, and it actually exploits water if there's too much. So this is the same concept just shown in graphs, okay? If there's too much, it'll do the high water intake. If there's less, it'll filter it out.
So it doesn't matter how hydrated you are, how much water you drink, this will always occur. There's always going to be equal amounts at the beginning, and at the end, they'll always absorb whatever is left over. What was the question? What was the question?
Can you repeat the part about what you were saying for equal?
Oh, the equilibrium?
Yeah.
Okay, so at the beginning, you have an equilibrium. So for example, in the proximal tubules, if you were to have, say, 70% of sodium, the amount of water that's in the proximal tubule will be exactly the same, so that you have this equilibrium. Because water follows sodium. Does that make
Now,
sense?
take that, now connect that to the function of the proximal tubule. No filtration happens in the proximal tubule. Therefore, there's an equilibrium, okay? See all this mess happening in the middle? That's where all the filtration is happening, and the reabsorption, the secretion, all that shebang. So, because there's nothing happening there, it's always constant. Whatever the sodium is the same as water.
Yeah, so in a steady state, water intake and output has to be equal. So you always want whatever you started with to be equal at the end. You don't want anything left over. That's why whatever water is left over is reabsorbed at the end.
Now, thinking about an exam question, somebody could ask you about dehydration. Somebody that clinically has something wrong with their hydration of their body. Use what you know here and what we'll talk about later on about water balance, and then you can hopefully end up answering a question that's related to some sort of defect that another person has. So these are the type of questions that you could be asked, okay? If somebody has a defect in their hydration, intake and output, if they're not equal, how does that affect the filtration? What falls apart with it? Which tubule falls apart? All that stuff.
Now, the loop of Henle is really important for the dilution and the concentration of your urine. So it functions to remove sodium chloride from the lumen and then it deposits it into the medulla. And it participates in forming dilute urine or concentrated urine. So essentially, what this image is showing is that in the descending limb, there's no ion formation. The only thing that happens in the descending limb is that you have water that is going out and into the capillaries. Now, as you go down the descending limb and up ascending limb, you have sodium chloride that is going out of the limb. So the amount of sodium chloride that's in the ascending limb is somewhat proportional to the water. So as you have sodium chloride exiting out into the medulla, you have water going into the capillaries. Now, just know that there's this like positive feedback. So the more sodium chloride that goes out, the faster the water gets out as well. So essentially, what I said, oh, hi.
Is any water reabsorbed in the ascending limb?
No.
So why does the image like make it seem like it gets thicker?
Oh, that's just the thick ascending.
Okay.
Yeah, so you have the thin deascending, thin ascending, and then you have the thick ascending.
So it's not because volume is more?
No. Well, technically yes, because now you should have more volume because you have more surface area, right? But that doesn't play a role in this loop. It doesn't play a role in this.
Okay. So the important thing I want you to know is that the descending limb is permeable to water, but ions can't go in it, right? And that's the first little part of the loop that you see. And then the second part, you'll have active sodium and chloride reabsorption, and there's no water that goes in. Now, the amount of sodium chloride that goes in is determining how dilute or how concentrated your urine is, because that directly affects how much water is coming out of the descending limb. Does that make sense?
So,
Oh,
sorry.
sorry.
Yeah, I'm just going. So the countercurrent multiplier system that was spoken of, yes.
I'm sorry to cut you.
That's okay.
You said like in the ascending limb, the solutes are getting reabsorbed, right? But the diagram shows that it's being filtered out in the thick ascending limb. I'm sorry, I was just confusing that.
No, you're right. What I was going to get to is that the countercurrent multiplier system, the feedback loop that regulates the loop of Henle, is through this idea, okay? So you have sodium going out, causes water to go out.
Yeah.
Sodium is still coming in here. So more water goes out, more sodium is getting pushed up, more sodium comes out. More filtration happens, more blood flow. This is the multiplier.
Sodium doesn't go into here. It goes
Sorry, yeah,
it
sorry,
goes into the
yeah.
space.
I just meant it exits, that's what
It exits. It doesn't go into the
Yeah.
descending. I
Yeah,
just wanna-
but it's a cycle, okay? So whatever's in here will increase proportionate to the amount of water,
There's more solute, right? More,
Exactly. okay? So that's somebody emailed us about counter multiplier system. That's the positive feedback loop. If you need to take water out more, you're gonna take out sodium more.
Essentially, the more sodium chloride, the faster this process happens. Not necessarily the amount of water, but the speed at which it happens.
And this kind of shows that. So you see how it's 400 throughout? So 400 is leaving, 400 is getting out of here. Whereas this is 200 and then it raises 400. So this can change, but it's proportionate to that. So it can get faster, it can filter faster, but through the secretion of water.
So yeah, summarize basically, the more transport by the ascending limb, so the more sodium chloride that gets reabsorbed into the medulla area, the more the concentrated the fluid is in the descending limb. So just
And
positive feedback, it just goes, the more sodium, the faster the water comes out.
so sorry about the lingo, but the limb is talking about the loop of Henle, okay? Don't get confused. When we say ascending limb, it's the loop of Henle. Use the actual terminology, I just forgot to change it on here, okay?
Alright, so now we have something like the vasorecta has this counter-current exchange. So this is, I want you to look at these images. So in image A, you have this like little straight thing. So if we imagine the kidney to just have a tube that goes straight. Everything that goes through this doesn't get reabsorbed the way that you would want. So you would have a lot more output coming out.
It's like a part of
But we've been involved to have this loop or this hairpin structure so that even though we are removing stuff in this side of the loop, it's kind of being regained in here. So we have this equilibrium kind of, and we have a little bit more output than what comes in, but it's not as drastic as, say, this. So it's just, I don't know if that makes sense.
Does anyone know where the vasa recta is located? Yes, exactly. So, back to the point I was making about how the anatomy controls the function. Vasa recta, how to work, here. This is your vasa recta, okay? It's surrounding your loop appendage. So this area is where that multiplier is happening. So first, within the tubule itself, you have the countercurrent system, and then within the vasa recta, you have another countercurrent system. So it's always regulating through the blood flow and through the tubules. So not only the urine is getting regulated, but the blood is also getting regulated. I think that's it.
So, yeah, basically the last thing, so if it was, I'm just gonna reiterate what I said. So if the vessels were straight, so if the vasa recta was straight and it was permeable, the blood flow would absorb all the solutes in water and wash out any hypertonicity that it would have. So the hypertonicity, as we know, the gradient is essential to know, like, to have concentrated urine. So that's why we have this hairpin structure, because we're not losing as much of the solutes that we have in our vasa recta. Does that make sense?
That is it.
Yes.
So, we just covered, I think we kind of covered 2 lectures. I think one was overlapping, so about 2 lectures of information. So the next week's tutorial will be covering the 2 lectures that are being taught this week. Yeah, that's, if anyone has any question, come up and ask us. If you want to address it now.
Yeah.
Go ahead.
You could put up your hand. Maybe other people would like to hear that question too. You never know. So if you have a question, you can ask it.
Is there a difference in the function between the thin ascending limb and the thick ascending limb? Is there a
That's a-
reason that it's thick?
I think it's, good question, but it is just for, so then more filtration can happen. Because if we didn't have this thick, this is where the solutes are coming out.
Mm-hmm.
So you have more volume in here, which means you have a greater chance of getting more solutes out. And if you can get more solutes out, you can start that positive feedback. So then you can increase the filtration rate faster as well.